So in this talk, we'll start to talk about the algebraic construction of local Langlands category. So this is due to Xinwen Zhu. So following yesterday's discussion about G isocrystals, this construction is more natural and in the realm of algebraic geometry. And its benefit is also that it's directly related to mod P geometry of, for example, Schumra varieties. For this talk, let's consider the category of perfect FP algebras. So this will be our test category. And then we'll introduce some notations. For any R, which is a perfect FP algebra, we'll denote by D of R, the spectrum of width vector of R, and then punctured D of R, so will be the spectrum of width vector of R with P inverted. So both of them has an action of this width vector forbiddeness, which I'll denote again by sigma of R as yesterday. And we'll fix some reductive group over QP. And LG will denote the loop group using the width vectors. Namely, it sends R to the W of R 1 over P valid points of G. And then we can introduce the main geometric object, which we call curly B of G. So this is the ℓ-sheavification of the quotient of LG by the sigma conjugation action of LG itself. So as a stack on CLG FP perf. So let me say that this at sigma means the sigma conjugation of LG on itself, namely sends an element to, the conjugation of this element, but up to as a sigma twist, sigma conjugation. And so this is what is called isoc in Xinwen's paper, and I'm choosing this notation. So this is borrowed from this paper Yin will talk about, and the reason for this is that this thing is slightly different from just the actual moduli stack of G isocrystals, which I will discuss in a minute. So I will make a remark on this in a minute. So, but let me also say that, so alternatively, you can define this as a fiber product in the category of étale stacks on perfect FP algebras by looking at, on one hand, the diagonal map from the classifying stack of LG to its self-product, and on the other hand, you look at the graph of sigma. So this is a fiber product. And this remark, why this is slightly different from moduli stack of G isocrystals is that you can easily see that there is a moduli interpretation of this construction, namely, once you sheafify this quotient as pre-stack, then you see that the datum of this LG point sheafifies to give you some G-tosser on on this punctured disk, and then together with Frobenius linear automorphism. But since we are doing an étale sheavification here, so there is so this G-tosser here I consider are all let's say Zariski tossers for the Zariski topology on this punctured disk. But we're étale sheavifying in R, so which means that étale locally on the base R, this E has to be trivial. But this condition is not automatic because we are not allowed to arbitrarily localize on D punctured of R, but rather just on R. So I think in general, one doesn't know whether it's true that for a general G-tosser, one can trivialize it étale locally on R. So, but in V topology, this is true, proven by Anschutz. So if we would sheavify this quotient in some finer topology, then this construction would be exactly the same as the moduli stack of G isocrystals, because that moduli stack doesn't have the last condition. But in the étale topology, we don't know they're the same. So at least a priori. And this, I will reserve this notation I saw for the actual moduli stack of G isocrystals, which is just for any R, you take the G tossers on D punctured over R, modulo out the Frobenius action. So. But for later talks, people should feel free to switch back. Okay. You can use other things as well, but. So maybe a priori this is FPPF. Okay, I don't know if it's the same, but oh no. Yeah. Okay, that's a good point. But even for Zariski tossers, I think. Oh, okay. Sorry. I have to check which one is. So at least for the FPPF ones, you can interpret them in terms of this Tanakan formalism. And since G is smooth, so FPPF and étale are the same. But maybe a priori it's not the same as Zariski. So I don't know. I have to check which one is actually used. Yeah, but even for Zariski tossers, I think we don't know if it's true that étale locally on R one can trivialize it. Yeah, thanks for the question. Okay, so the next thing we want to study is the geometry of the stack curly BG. And the main result about it is the structure of a Newton stratification on it. So for this, we have to consider this lemma. So namely for any algebraically closed fields and an extension of algebraically closed fields in characteristic P, the natural map on K1 points of BG to K2 points of BG is an equivalence of groupoids where the set of isomorphism classes are both identified with BG. So this is not hard to prove once you know that BG is invariant under algebraically closed extensions. So I will skip the proof of this and leave it as an exercise. You can also read it in Xinwen's paper. Okay, but using this, one can make the following definition of subfunctors of BG attached to elements in the Cotwitz set. So, namely, one can define a subfunctor of curly BG as saying that if a point of BG factors through this subfunctor, then so this is equivalent to, for any geometric point on the test scheme, the isomorphism class of this test object as an element in BG using this lemma agrees with B. So. And similarly, one can define subfunctors with smaller or equal to conditions where the partial order is the one introduced yesterday for the Cotwitz set. Okay, so for people who have seen similar constructions in the Bang-G setting, so this is certainly not surprising, and it's probably familiar. And the main result regarding these Newton stratification, so this is 3.31 in Xinwen's local Langlands paper, is that so if we base change BG to FP bar, then one can describe the stratums explicitly. So maybe, perhaps, in fact, I didn't have to base change for all the statements, but only the last statements. But nevertheless, let me write it this way. So, so first of all, these inclusion maps. If I take the less or equal to conditions, then this is close immersion, and it's perfectly finitely presented. And so this condition of morphisms, or this property, will show up a lot in this setup of Xinwen, and it will be abbreviated as PFP. And second, so the closure relation in the stack BG is the same as the closure relation in the Cotwit set, or even so yeah, or even even more precisely, the underlying topological space of this curly BG agrees with the Cotwit set equipped with the order topology explained yesterday. And the third one is slightly different from the analytic setting, so namely these inclusion of the B stratum into the smaller or equal to B stratum is an affine open immersion. And in particular, this map is quasi-compact. So in the analytic setting, so in Bangji, such statements will be completely false, and which causes also a lot of problems. So this one is the more interesting one in the scheme case. And the last one, for the purpose of discussing representations, so the last one is that for each individual stratum, once we base change to FP bar, we can identify it with the classifying stack for this topological group coming from the QP points of GB, so the sigma centralizer of B, and the pro-étale topology. So, so note that this is still an étale sheaf, except that for a test object, it classifies pro-étale tossers under this group. Okay, the proof is basically follows from results on the generations of isocrystals in families. Although this BG, as I said, is not completely the same as moduli stack of isocrystals, but you notice that if you look at the actual stack of G isocrystals, it receives a map from BG by just forgetting the condition that this E can be étale locally trivialized over R. And then this Newton stratification is, of course, already defined on isoc. And so all the statements stated here, you just have to prove for isoc. And then you can use results about the generations of isocrystals in literature. So the first part and the second part regarding this closure relation, this is due to Grothendieck. So it's actually Grothendieck's specialization conjecture and cuts. And in the setup of isocrystals with G structures is due to Rappaport and Richards. This affineness of this map, this is something special, and it uses the purity of Newton stratifications for F isocrystals. So so this was originally studied by Dion Art, and then many people, and in this generality, in a paper of Hammerher and Kim. So this is called a purity result because the original statement of this result, Dion and Art proved, is that something of the following flavor. So if you look at a Noetherian local ring whose dimension is greater or equal to 2, and then if you have an isocrystal which has constant slopes apart from the closed point, then it has to have constant Newton polygons on the whole thing. So Noetherian local ring, characteristic P. So in other words, this constancy of Newton polygon extends over codimension 2 loci, so which is why this result is called purity. So MP here stands for Newton polygon. And this this of course says that if you have a jump of the Newton polygon, then it has to happen in codimension 1. But then you have to work a little more to show that it's actually affine. So the open immersion is affine. So this shape of the stratum, this basically the thing you wished about seeing representations. So therefore, you would hope that if you consider ℓ-adic sheaves on the stack, you will be able to see representations of these groups that you're interested in. And this result is true in both Xingwen setting and Fargues setting, but the proofs are different. So here, so one can construct a map from the left to the right by just looking at such a element in BG, which correspond to this this vector bundle, this G bundle on the punctured disk quotienting out forbiddeness, and you can look at the Proital sheaf of trivializations of this thing. Where EB phi B is the isotrivial G bundle on this quotient. So this quotient, I view it as a functor. So plugging R, it gives me this punctured disk on R, quotient out forbiddeness. So obtained by pullback along the map from D star quotient Z to, so D star over K, so we recall that K is FP bar, so this is the reason why I have to restrict to FP bar algebras, so that plug in every R, so there is a map like this. but when K is R, so G bundles on the target is, sorry, when R is K, then G bundles on the target is just classified by the usual Cartwright set. So in particular, fixing an element B, I can define some G bundle on this thing, and I can pull back to get a G bundle on the source. And so, and now this thing clearly has an action of the automorphism group of the second bundle. And so viewing it as a sheaf on perfect FP algebras, this is the same as this Breuer sheaf attached to this topological group. So therefore, this construction already gives you a quasi-tosser. And the non-trivial part, input of this proof is that this is actually a tosser. So the sheaf has pro-étal locally a section. So this is result due to Art zinc. Wait, let's do this. Karian-Nishotsu. So in different generalities, and the one used here is again Hammer-Kim. So the key of this proof is that if you have a fiberwise on the base, so if you have an F isocrystal that is fiberwise on the base has constant Newton polygon, then pro-étal locally it can be already defined over some finite field. Okay. Okay, so this is results about Newton stratification. The next thing that is used to study both the geometry of the stack curly BG and the sheaves on it is the existence of some nice chart. So so this is an int perfectly finally presented proper chart. So so first recall the definition. So a map of étal stacks on perfect FP algebras is called int PFP proper, or generally other properties, class of properties. If so, for any perfect scheme over Y, its pullback has a presentation as a colimit with nice transition maps, and each thing appearing in the colimit is a proper map over the base. Hmm? You mean the test object?
Yes, and also the pullback should also
be algebraic. But even if I restrict my stacks just on perfect FP algebras?
Yeah, so even if you can pull back by a perfect FP algebra, but the pullback might be an algebraic space.
Ah, okay, yeah. In terms of representability, okay, thanks. Okay, let's do this. Thanks for the comment. Algebraic space. then so this thing is so this pullback should again be an algebraic space, and so this has a presentation as the, wait, sorry, do I have to add an int here? Okay, let me write it this way. This pullback has a presentation in terms of colimits of maps over S. So where the transition maps are perfectly finally presented closed immersions, and each xi over S is a perfectly finally presented proper map. So these are algebraic spaces. And this property is can be checked at tau locally on the target. So tau local. The test object can be taken to be, sorry?
So we don't have to take any algebraic space, perfect algebraic space of S.
So yeah, I think for test objects you don't need, and then but for these things you probably. So I think Ian's remark is that in general I should enlarge the category I look at instead of just considering schemes. I should allow algebraic spaces. So the map itself doesn't have to be representable in schemes. Yeah, thanks. Okay, so right. So then we want to construct an int PFP proper chart of curly VG. For this, we'll consider the moduli stack of Stukas. So which depends on a integral model of G. So we fix some parahoric model of G and call it curly P. So and then one can define the positive loop group attached to P by sending R to the value of P and the width vector sub R. And then one can define width vector affine correspondence flag variety by taking the sheaf quotient of LG by L plus G. So this will be an int projective scheme over FP. And this will be the source of this int PFP properness in the end. And then we can consider the moduli stack of local Stukas by taking an Étale sheafification of the construction as before, but where you replace the sigma conjugation of LG by L plus P here. So alternatively, so the moduli interpretation of this is that you send a test object R to the groupoid of P Stukas over R, and i.e. just a pair E and phi, which is similar to isocrystals, except that here you require E to be a G bundle, a P bundle, sorry, on the whole disk, so without the puncture, and that's why you need this integral model of G. And then phi is a meromorphic map from sigma pullback of E to E, where it's an isomorphism when you restrict to the puncture disk. Okay, and note that here we don't need to impose the condition that that E is étale locally over R trivial, because this will be automatic. So note that the difference with before is that so this width vector of R is complete along R. So in particular, so this if I use R to denote this kernel, then this form, so W and I form a Henselian pair. And we know that this means that as étale sheaves, sections over the closed fiber is the same as the section over the whole thing. Well, since this curly P is smooth, so étale local and smooth locally are the same. So. Okay, so and then this also tells us that for the previous problem regarding whether an isocrystal is étale locally on R trivial, this is mostly a question about whether one can étale locally on R extend this D cross, this G tosser over D cross to D. Okay. So now, once one has this moduli of Stukas, one can define a map. So either just using this presentation of the stack, or using the moduli interpretation, one see that there is a natural map from this thing to BG. So in terms of the moduli interpretation, this sends this E phi to the restriction of it to D cross. Okay. So then the most important property of this map is that this is int PFP proper and surjective, and we need this property because of the sheaf theory we consider later. And the case of like the ℓ-adic sheaves that one define on these pre-stacks on perfect FP algebras, they satisfy descent for this kind of covers. So and the proof of this, as I just said, not too hard, by relating the fibers of this maps to these affine flap varieties. So, namely, given a test object of BG corresponding to some G isocrystals E comma phi. So we know that by the condition that this is a point in BG, we have an étale cover of the base that trivializes the underlying G tosser. So therefore, if we consider this map, so which is called NT, by the way, it stands for Newton polygon, Newton stratification. So if now one pull it back all the way to a spec of R prime, then you see that the fiber in terms of the moduli interpretation would be just giving a G-tosser on D of R prime with a trivialization of the star R prime. And this is, in fact, just a moduli description of the affine flat variety for P. So here, let me. And and we know that this map, as we said before, is in projective, so in particular in PFP proper. So we can draw the conclusion. And one should also say that this proof, where we used the fact that ℓ locally on R, one can trivialize this underlying G-tosser, is precisely the reason we prefer this sheavification construction, ℓ sheavification construction of BG, rather than just take the moduli stack of G-tossers. G isocrystals. Right. So maybe another remark, which I can say orally, is that so another reason to consider this cover is that on the source, the moduli stack of P Stukas, there is a stratification in terms of double quotient involving the affine Weyl group. And so if you fix a stratum there and then restrict this map to that stratum, then the fiber of that map will give you affine delinguistic varieties. So the last thing I want to discuss is, so now ℓ-adic sheaves. On BG, so maybe mostly just the abstract construction of ℓ-adic sheaves in the setting. So you want to consider coefficients that are either finite or error complete, whose quotient is finite, or localization of that, or co-limits of these things. And the basic goal for the purpose of performing this this geometrization of the local Langlands on BG, you want the following things to hold. So first of all, so we've identified the stratum in BG, and you probably want to identify sheaves on these classifying stacks with smooth representations. So more precisely, in the end, what will be true is that this will be the same as the left completion of the usual derived category of smooth representations of GQP on lambda modules. And a second thing is that, so maybe I want to say that you need to define this sheaf. And the second thing is that you hope this definition satisfies some descent result. So for example, this int PFP proper descent. And then hopefully it upgrades to sex functor formalism. And then the third thing is that you want there to be a semi-orthogonal decomposition on BG given by excision. So that you can describe the whole category of ℓ-adic sheaves on BG in terms of these representations. So let me just make a remark on, so even one is pretty tricky to achieve, in fact. So because a naive approach, so say in the case of localization of some arrow-complete rings as a coefficient, so you would the naive approach is that you consider for lambda 0 for lambda 0 you consider some ℓ-adic completion of the torsion categories, so where the usual étale sheaves will already behave quite nicely. And then for lambda, you just pass to the isogeny category. So which basically means that you quotient out bounded torsions. But then there is a basic issue is that so this passing to isogeny category doesn't kill unbounded torsion, and so for schemes, if you pass to some subcategory with finiteness properties, let's say constructible sheaves, bounded constructible sheaves, then you can resolve this issue of unbounded torsion. But however, in terms of stacks, the classifying stacks for these profinite groups, etc., you can naturally encounter some smooth representation and even admissible representation that has unbounded torsion. So maybe let me say just a very basic example. If you take these torsion module, take a direct sum of z mod L to the n's, and then you'd want, in some cases, to make constructions like tensoring with QL in the usual category of ZL modules to kill these torsions. But if you are forced to, if the category you consider is forced to be arrow complete, then in the arrow completion of this torsion module, you build up some free part. And in this case, so tensoring with QL will not kill this. So which means that so yeah, this one, okay. So yeah, which will sometimes cause you a problem. Okay, maybe let me don't expand more on this, because right now I don't have a precise context to tell you what is so bad about this. But this is a natural problem you actually encounter, and also this question is present also in the analytic category. so where the issue pops up because you encounter more situations where the maps are not quasi-compact. So it's more likely that you have sheaves which are have unbounded torsion. Okay, this is a side remark. But the actual construction that would resolve this in the scheme case, or in the algebraic case, it's slightly easier than the analytic case. So here, what you do is that you first consider quasi-compact, quasi-separated perfect schemes or algebraic spaces. And let's do the situation where it has a structure map to some algebraically closed field as a base. Then the first step you do is to write your x as an inverse limit of perfectly finitely presented schemes and where the transition maps are all affine. So this is always possible for QCQS algebraic spaces. And so for these PFP things, you just consider the incompletion of the usual bounded constructible sheaves. But then on the bounded constructible sheaves, you pass to the opposite category. And the reason for that, I will explain in a remark later. So here, on the bounded constructible category, it is really the inverse limit of the torsion things when lambda is arrow complete, and then passing to the isogeny category if lambda is something like Q arrow. And then on X, you take a left Kahn extension. So, and concretely, this means that you take the co-limit of these sheaf categories, but with transition maps given by Schrick pullbacks upper. So, yeah, so when I say Kahn extend, I will have to view the construction of sheaf with lambda coefficient as some functor, and then here the functor we're using when there is morphism between x and y is the upper Schrick. And note that since lower Schrick preserves colimits, so these upper Schrick functors on these categories are defined. So I think on the bounded constructible is the same as the opposite. Yeah. Right. So you can also directly define this as the K-linear dual of the so-called sheaf star category. Yeah, and because that thing is compactly generated, but this one is more down to earth maybe. Okay, and then in general, so you have to show that this construction upgrades to some nice functor on correspondences, and then you can do a right Kahn extension to extend to all pre-stacks. So maybe the last part, I'll just be a little vague. So, but again, this right kind extension more concretely will be just the limit of the sheaf categories of QCQS perfect schemes, or maybe I need to extend to algebraic spaces if I want the prestacks or to be correspondences on algebraic spaces, but let me ignore that. So again, and then the transition maps are again by Schrick pullbacks. Okay, so let me, so my time is essentially up. Let me mention a few things about this construction. So the first thing is that note that this construction actually depends on the structure map from X to the base field. And so the property of this sheaf category even depends on the base field. So right, and then a second thing, which is the main reason that we use this Schrick functors and the opposite category. This is when X is some nice int scheme, then one has a better control of this category. So in particular, this sheaves on ℓ-adic sheaves on X is the same as colimit of the sheaf categories on these X alphas with transition maps by star push forward. So this is the main reason why we need to pass to op, because this will not be true on the the dual sheaf category and using star pullbacks. Right, and then it has universal descent for int PFP proper surjections. And maybe the last thing I want to tell you is that it resolved the problem that I said at the beginning, because so even when X is just a point, you notice that this sheaf category, let's say lambda is ZL or QL, this is really just int perf lambda, because so X itself is PFP already, and this int bounded constructible becomes int perf, and this is the whole category of lambda modules where lambda is considered as a discrete ring. So it's not the L-complete category if L is an L-complete thing. So, which means that you can actually perform the operation of tensoring with QL in this category, and which is important. And the last thing is that, so when X is the classifying stack of some profinite group, that allows, that emits a lambda valued Haar measure. Then the map from a point, so H is back of FP bar. So I will stop after finishing this example. This satisfies universal homological descent, so which means that the category of sheaves on X with lambda coefficient will be the limit of sheaves along the check nerve of this map. So, and here I need, and in particular, this relates to just smooth representations of K, so as you wished. And the proof of this is basically using a Barbach-Lurie, where you have to check that upper shriek is conservative and reflects limit diagrams, so basically. But let me say that as a warning that you might be a little confused because if you take the check nerve, then sorry, there are too many arrows. And then you might thought that this should be some formal. This result should follow formally from the definition of sheaf as right Kahn extension on like when X is a stack like this, because. But then the problem is that because as a like if you have a stack. That is a co-limit of such diagram, then by the definition of sheaves as right Kahn extension, the sheaf category on the stack will automatically be the limit of the sheaves on terms in this check complex. But however, the problem here is that this does not apply to X because the problem here is that the co-limit of this thing is BK, but not the same as X, because this BK is really the classifying stack of K in this maybe étale topos, but X is some sheafification of it in terms of pro-étale tossers. Yeah, so maybe just let me stop here. Sorry for going over.